Hello, this is M.Leitgab from the University of Illinois at Urbana-Champaign in the United States of America. I would like to thank the Space Generation Advisory Council and the main award sponsor Space Canada to give me the opportunity to present my paper, which was selected as the winning entry in the SJC Second SSP International Design Competition. The title of my talk is Exploring Hypermodular Self-Assembling Space Solar Power for the Goal of Midterm SSP Deployment. The focus of my studies is to explore the potential of satellite self-assembly based on a highly hypermodular architecture. The concept should avoid the dependence on in-space assembly infrastructure and thereby reduce cost and resources for SSP development and possibly allow earlier SSP deployment. The technology assumptions and choices made in my study include electricity generation through photovoltaic cells, wireless power transmission through 2.45 GHz radio frequency microwaves, and on-orbit self-assembly performed through spring-loaded interconnects, electric motors, inflation, or rollout mechanisms. The main platform architecture approach follows the sandwich module concept. A typical sandwich module design is shown in the lower half of the slide. At first, I studied options for low Earth orbit SSP demonstrators with a self-assembling design approach. Assuming that fully autonomous self-assembly is realistic for sufficiently small systems, I limited the maximum size of single SPS to the payload capacity of current launch vehicles, such as the SpaceX Falcon 9. The base units of the main platform are hexagonal sandwich modules with a diameter of 4.4 meters and an area of 13 square meters. On the left, you can see a depiction of the Falcon 9 payload volume, of which about 70% are filled with sandwich modules stacked along the vertical axis. The remaining volume is allocated for all other satellite subsystems. I determined the power levels of single SPS from sandwich performance parameters achieved in current sandwich integration studies. I assumed an improvement of those parameters by 20% for a near-term LEO demonstrator, arriving at an area-specific mass of 16 kilograms per square meter, a sunlight to RF efficiency of 15%, and a sandwich height of 12 centimeters, including protective packaging. This yields a nameplate RF power output of 120 kilowatts for a SPS launched on a single Falcon 9. The obtained power is limited by the launch mass capacity of Falcon 9 vehicles. Here you see an illustration of a LEO demonstrator SPS from a single Falcon 9 launch. The sandwich modules are arranged to form a square main platform of about 26 meters side length. The reflector arrays are only given for completeness or of pure symbolic character. Finally, I performed an order of magnitude cost estimate for research and development, test and evaluation, and production cost of all systems. The estimate includes cost for the sandwich modules, generic satellite subsystems, reflector arrays, and self-assembly mechanisms for 2 demonstrators, in addition to cost for 2 Falcon 9 launches and a ground antenna sized for 95% power coupling. The total cost is estimated to be about $1.9 billion. Next, I would like to report on studies I performed for midterm SPS constellations delivering utility-scale power, also based on self-assembling SPS launched on single launch vehicles. I assumed midterm technology advancement to improve current sandwich performance parameters by 40%, yielding an area-specific mass of 12 kilograms per square meter, a sunlight to RF efficiency of 17%, and a sandwich height of 9 centimeters. For self-assembling designs in high-capacity launch vehicles such as the SpaceX Falcon Heavy, the sandwich module height is found to be a critical and currently limiting parameter for vehicle integration and sizing of SPS. With the parameters mentioned, a SPS launched with the Falcon Heavy launch vehicle would achieve an RF nameplate capacity of about 630 kilowatts, assuming 3 sun concentration. Here the obtained power is limited by the launch volume capacity of Falcon Heavy vehicles rather than the launch mass capacity. To also avoid relying on orbital transfer infrastructure between LEO and geostationary orbit, onboard electric propulsion thrusters with a specific impulse of 3,000 seconds are used. The orbit transfer is expected to require about 4 tons of propellant, and the thrusters are powered by 10 auxiliary PV modules delivering about 30 kilowatts of electricity. The SPS is fully deployed upon arrival at GEO. On this slide, I show illustrations of a possible arrangement of the sandwich modules from a single Falcon Heavy launch, forming a strip of 70 meters length. The symbolic reflector array is sized to achieve 3 sun concentration on a photovoltaic surface. 5 SPS are connected to form a square supermodule with main platform side length of 70 meters. To deliver utility-scale power, these supermodules are arranged to form a continuous circular area when viewed from Earth. Only the supermodule sandwich platforms are shown on this slide, corresponding to the smaller red squares. The given constellation has a nameplate capacity of 1 gigawatt RF power and consists of 1,600 single SPS launched by the same number of Falcon Heavy vehicles. The supermodules are connected in strings along the north-south direction. To reduce self-shadowing of the sandwich platforms and reflector arrays, the north-south strings are staggered at different orbital altitudes. The umbra of a SPS string dissipates about 30 kilometers behind the string. This is where the next string is placed. The depiction on the bottom of the slide shows the first half of a 1 gigawatt RF constellation as viewed along the north-south direction. The strings of sandwich platforms are indicated by red bars, the corresponding reflector strings by gray bars. However, further study after submission of the paper revealed that the constellation with staggered strings suffers from stability problems. Due to the large radial distance between the innermost and outer strings, the continuous circular shape as seen from Earth can only be sustained on a constant acceleration of the outermost strings of up to 500 newtons. This does not seem feasible in the context of current technology and SPS lifetimes on the order of 10 years. To summarize, the potential of self-assembling SPS has been studied by limiting the size of single SPS to the payload capacities of current and near-term launch vehicles. Two scenarios are evaluated. First, 2 LEO demonstrator satellites yielding 120 kilowatts of RF power each could be deployed to a 300-kilometer orbit by 2 Falcon 9 launches. Including a ground antenna, the total cost for development, production, and launch is estimated to about $1.9 billion using a learning curve method. Second, midterm SPS systems for utility-scale power are studied. Sandwich module height is identified as a critical parameter limiting the size of single-launch SPS. Onboard electric thrusters are used to avoid the need for orbital transfer infrastructure. The nameplate RF power of single SPS launched on single Falcon Heavy vehicles is found to be 630 kilowatts at 3 sun concentrations. This allows the formation of a 1 gigawatt RF utility-scale power constellation by 1,600 SPS. A similar learning curve approach as above estimates the total cost for development, production, and launch of the 1 gigawatt RF constellation to about $15 billion. Future efforts are directed to improve the formation stability of the utility-scale constellation architecture. This was my presentation. Thank you very much for your attention.